I'm Alan Fenn at MIT Lincoln Laboratory, and this is lecture number 5, Focused Near-Field Testing of Multiphase-Center Adaptive Array Radar Systems. This lecture is part of the lecture series Adaptive Antennas and Phased Arrays. Here's the course content breakdown by topic. This is lecture 5, which is going to be covering adaptive antenna theory in the context of jammer nulling and radar clutter suppression. We'll be covering some phased array theory. This would be considered an antenna measurement technique. We're going to take into account array mutual coupling and do computer simulations for the far field and near field. This lecture is based on Chapter 5 of the book Adaptive Antennas and Phased Arrays for Radar and Communications. So the purpose of this lecture is to describe a focused near-field adaptive nulling technique that can be used to evaluate the far-field performance of an adaptive phased array radar system. In the previous 2 lectures, we had investigated the focused near-field adaptive nulling technique for the case of a linear array with jamming and no mutual coupling. That was in lecture 3. In lecture 4, we looked at the case where we had a linear array and we included the effects of array mutual coupling. Now in this lecture we're going to take into account not only the array mutual coupling, but we're going to have multiple phase centers, clutter, jamming, and target signals included in the analysis. Here's an outline of the talk. After a brief introduction and background, we'll cover the theory for the focused near-field adaptive nulling simulations, show you some results, and then summarize. So by way of introduction, adaptive antenna systems have been explored extensively by numerous researchers since the 1950s, and the primary functions of an adaptive antenna system are to minimize or null interference and jamming, to suppress radar clutter, and detect radar targets. So in this lecture we're going to address an adaptive phased array antenna system that will need to detect a target signal and minimize radar clutter and minimize radar jamming effects. So we'll be analyzing a multiphase-center antenna, and we'll be describing the signal processing used to eliminate the undesired signals, the undesired clutter and interference, and show how to detect the desired target. So in this slide we're showing considerations for testing a large adaptive phased array antenna. Now if we have a large adaptive phased array antenna with multiple interference sources, this can be a difficult configuration to test because the far field distance, r equal 2 length of the aperture squared divided by wavelength, can require long test distances. For example, a 20-meter aperture at 1 gigahertz would require a 2.7 kilometer range distance. If we go up to 10 gigahertz, the range distance required is 27 kilometers. And if we have multiple interference sources widely separated in the field of view of a large adaptive antenna, it would be very difficult to do far field measurements. So an alternate test configuration that reduces the test distance is very desirable. And so we've discussed this technique in the prior 2 lectures. So this slide shows the focused near-field adaptive radar antenna system testing concept, where we would position a large adaptive phased array aperture inside of an anechoic chamber. We would use near-field focusing to form a main beam and side lobes away from the main beam, which would look similar to a far field pattern. We would then introduce jamming sources in the side lobes of the antenna, and then clutter and target sources in the main beam region. The signals from the receive antenna would go to an adaptive nulling receiver and signal processor, which would then control the antenna in such a way to form nulls in the direction of jamming, suppress the clutter signals, and detect the target signal. So this technique allows real-time measurements of adaptive radar system performance. This can all be done in a ground test facility prior to deployment of a phased array radar. So let's go through the theory. Here's a comparison of antenna test regions. The far field region, the the Fresnel region, which is between the far field and near field regions. We're going to concentrate on the focused near field region in this talk, which is between 1 and 2 aperture diameters from the antenna under test. Another technique which is commonly used to evaluate phased array antennas would be the planar near field scanning technique. But the planar near field scanning technique is not a real-time technique and would not be useful for adaptive nulling measurements. This slide shows a comparison of far field and near field sources for an adaptive array. A far field source would generate a plane wave signal impinging on the array, and a near field source would produce a spherical wave incident on the array. Now, if we examine the dispersion or time delay for near field and far field sources, and we express that in terms of a normalized dispersion multiplier, as shown here, which is essentially BL over C times the path length difference between the endpoints of the array and the source, normalized by the length of the array. So when the source is at infinity, the normalized dispersion follows a cosine curve, and when we're at range distances from 1 to 2 aperture diameters, there's very little difference between the near field and far field dispersion. We do see some larger differences once we get down to about 1/2 of an aperture diameter. So we would conclude that near field dispersion is approximately equal to far field dispersion when the source distance is about 1 to 2 aperture diameters from the antenna under test. So this slide shows a little more detail on how the focused near field adaptive nulling test concept might work. Here we have the large phased array antenna aperture with the focused array pattern superimposed. To form the focused near field pattern, we have a set of TR modules with weights, amplitude, and phase that can be used to calibrate the phased array to a focal point. We can introduce a CW radiating source in the band of the radar and then change the phase settings to maximize the signal received from the CW calibration source to form a focused beam. So we'd have a focused main channel output. We can tap off a number of auxiliary elements, forming a side lobe canceller or a partially adaptive array. So we have a number of weights that are used in the adaptive nulling process. So we can have jammers in the side lobe region, and we can have clutter and target in the main beam region. Now we're showing this on a planar near field test plane, which might be compatible with conventional planar near field scanning equipment. As an example of near field source deployments, here we're showing a 60-degree field of view and a 120-degree field of view. And clearly, if we want to minimize or keep the source deployment length as small as possible, we want to come in as close as possible to the array. So with a 60-degree field of view, when the F over L ratio, the focal length, is 2, then the scan length has to be 2.4 times the aperture length. If we come into a focal distance of 1 aperture diameter, then the scanning length or source deployment length is 1.2 times the aperture length. So if the field of view is 120 degrees, we require a scanning length of 7 times the aperture length if we're at an F over L ratio of 2. If we can bring the F over L ratio into 1, then the scanning length or source deployment length is 3.5 times the aperture length. So to summarize, the source deployment length depends on the field of view and the range distance, and to reduce the deployment length, it's desirable to reduce the test distance. Now let's review the Displaced-Phase-Center antenna radar system approach to suppress jamming and clutter and detect moving targets. So we covered this before in lecture number 2. So let's consider 2 displaced phase centers A and B, and we're going to transmit from the full aperture at points A and B corresponding to the pulse repetition interval, the PRI. So on the first transmission, Here's the array, and we're forming a phase center at position A using the full aperture. And then 1 PRI later, when the array has moved, we then are transmitting from the full aperture at position B. So we're sending out a series of pulses. We're trying to detect a moving target in the presence of stationary clutter and in the presence of jamming. So on receive, we're receiving signals from the stationary ground, the moving target, and jamming. So we start out by receiving initially at phase center position A, and then when the next pulse comes back, separated by the PRI, we move the phase center back to position B. And so what we're doing is forming an equivalent monostatic radar location, denoted AB, at this point shown here, such that the radar sees stationary clutter, and that can be canceled. And so we're able to detect the moving target because of the change in phase that occurs in 1 PRI. So this slide shows the displaced phase center antenna and adaptive beamformer. Consider an n-element array, and from each antenna element we split the signal into two paths, one to phase center B and one to phase center A. Each of these phase centers contains a set of amplitude and phase modules, or TR modules, and a combiner. So we're basically forming an array output B and A, and a set of auxiliaries that are used in suppressing interference. We then have a set of adaptive array weights in each phase center that are controlled by the adaptive processor, such that at positions B' and A', the jamming is canceled. And once we do a final summation of the two phase centers going through the adaptive phased array process, we have the jamming canceled and clutter canceled and the target detected at this output shown here. So to summarize, the jammer signal is nulled at points A' and B', and the clutter is nulled and the target is detected at the final summing junction output. Now this slide shows a near-field source positioning for a displaced phase center antenna. Here's the large DPCA antenna system with two phase centers. And what we want to do is have a set of digitally controlled sources in an anechoic chamber, preferably, such that we distribute a number of sources on the main beam, making it look effectively like radar clutter. We would embed a target signal here as well, and then we'd place a jamming source in the side lobes of both phase centers. So there's two sets of sources, a set of B sources and a set of A sources, corresponding to each of the phase centers in the adaptive antenna system. This slide shows how we do the analysis. Consider a receive array with mutual coupling effects analyzed by the method of moments. Here's the receive array. Each of the elements has a receiver behind it. And what we want to do is, in this case, simulate or calculate the received voltage at each receiver element due to a near-field source, which can be jamming or clutter or target. So the array has mutual coupling expressed by the open circuit mutual impedance matrix elements, ZMN. These can be calculated, and an open circuit mutual impedance matrix element between the jth near-field source and the nth array element. So we want the voltages received by the nth array element due to the jth source. We compute the received terminal currents for the nth array element due to the jth source. We compute the open circuit mutual impedances between all the elements of the array. And then we also compute the open circuit mutual impedance between the nth array element and the jth source. Once we do that, we form a mutual impedance matrix which can be inverted, then multiplied by the open circuit voltage received at each of the elements due to the jth source, solving then for the received voltages. And these voltages are used in the adaptive array process. So what we need to do is compute the covariance matrix elements for near-field and far-field interference. Cross correlations are expressed in terms of the expected value of the product of the voltages in the mth and nth channels. So the covariance matrix element R sub mn can be expressed as the frequency average shown here as 1 over the bandwidth integrated over the nulling band of the product of V sub m times V sub n conjugate. So V sub m takes into account the wavefront shape, which can be spherical in the near field case or planar in the far field case, because we're going to want to compare near field and far field nulling. If there are multiple interference sources and they're uncorrelated, we can simply sum up the covariance matrices for the individual sources as shown here. If there are j uncorrelated sources, we sum up the covariance matrices and add in the identity matrix to represent thermal noise for the adaptive nulling receiver. The adaptive array weight computation is done as follows. Prior to generating an adaptive null, the adaptive channel weight vector is chosen to synthesize a desired quiescent radiation pattern. And when interference is present, the optimum set of weights to suppress the interference is computed as follows. We invert the covariance matrix and then multiply that result times the quiescent weight vector, which gives us the adaptive array weight vector. To compute the array output power and interference noise ratio, we can do the following calculation. So the expected or mean value of the adaptive array output power is shown here, and that's given by the weight conjugate transpose times the covariance matrix times the weight vector. That gives us the array output power. Now if we want to know the interference noise ratio, that's computed from the ratio of the output power with the interferer present to the output power with only the receiver noise present, as shown here. So it would be the weight conjugate transpose times R times the weight vector divided by the weight vector conjugate transpose times the weight vector. Next, to compute the adaptive array cancellation ratio, we define that as the ratio of the interference output power before adaptation to the interference power after adaptation. It would be P sub Q divided by P sub A. And so the cancellation ratio is the quiescent weight vector conjugate transpose times the covariance matrix times the quiescent weight vector divided by the adapted weight vector conjugate transpose times the covariance matrix times the adaptive weight vector. The covariance matrix eigenvalues represent the degrees of freedom of the adaptive array process. The covariance matrix has n eigenvalues and n eigenvectors, which can be expressed in this form shown here. By the spectral theorem, the covariance matrix, which is Hermitian, can be decomposed in eigenspace as the following summation. R equals summation k equal 1 to n of lambda sub k times ek conjugate transpose, where lambda sub k is the kth eigenvalue and ek is the kth eigenvector. So since the covariance matrix is Hermitian, the eigenvalues are real, and the sum of the diagonal entries of the covariance matrix is equal to the sum of the eigenvalues. The eigenvalues, or degrees of freedom, are proportional to power. These eigenvalues represent the degrees of freedom that are consumed in the adaptive nulling process. So we can use these eigenvalues to compare the degrees of freedom consumed by near field and far field sources. So let's show some results. So we're going to simulate a large adaptive displaced phase center antenna. So we're going to analyze a dipole array with mutual coupling. So the elements are spaced in 0.473 wavelength intervals. The active portion of this large array spans 15.61 meters. And the complete array with terminated elements, there are two elements on either side of the long linear array. That array spans 16 meters. There are two displaced phase centers fully split apart. We're going to have element weights with 5 bits control and RMS errors of 0.3 dB and 3 degrees. We'll use 7 auxiliary nulling channels spread across the array in each phase center. We will take into account array mutual coupling effects by the method of moments. We're going to analyze single jammer and multiple clutter sources for near field and far field cases. This array operates at a center frequency of 1.3 gigahertz and has 1 megahertz of nulling bandwidth. And we'll be showing radiation patterns before and after adaptation in the near field and far field, as well as the adaptive cancellation and covariance matrix eigenvalues. Here's the geometry for the dipole receiver array and the dipole source antenna that's used to illuminate the array. So we've got a long linear array of 148 elements. 2 elements on the left and 2 elements on the right are simply terminated to minimize edge effects. We saw some of the edge effects of a DPCA array in Lecture 2, and we showed that having passively terminated elements on the end of the array helps match the phase centers and to get improved clutter suppression. So a transmitting dipole source is located at a distance d away from the array. So in this example we have 144 received dipoles in a linear array surrounded with 2 terminated elements at the array edges. So here we're showing the simulated displaced phase center antenna amplitude distributions of the 2 phase centers. So it's a 16-meter aperture. We have phase centers A and B. We're using a minus 40 dB Chebyshev illumination function to get low side lobes. And so plotted here is the amplitude versus element position for the 2 phase centers. And so we split the phase centers apart to 7.86 meters, or almost half the aperture length. And so we see that in phase center B and A we see similar patterns, but they're not identical because of the TR module effects. And so phase center A has the amplitude on the right side, and so the left set of TR modules has been turned off. In phase center B we see the illumination on the left side of the array, and the TR modules on the right side of the array in phase center B have been turned off. This slide shows a simulated near-field probe scan for 2 DPCA phase centers before nulling. So this is a 16-meter dipole array at 1.3 gigahertz with a minus 40 dB Chebyshev illumination function, and we've scanned the main beam to minus 30 degrees from broadside. We scanned the beam to the left as shown in this diagram. And so with phase centers separated by 7.86 meters in the focus near field region at f over d of 1, we would expect to see 2 beams, one for each phase center, separated by the phase center displacement. That's what we see here. Here's phase center A, main beam and side lobes, and then phase center B, near field radiation pattern, main beam and side lobes. So what we want to do next is take these 2 simulated focus near field radiation patterns and convert these, instead of in probe position x in meters, we want to convert this to angle in the near field. And that's shown here. This is the focus near field radiation patterns for 2 phase centers before nulling. And now that we've converted to angle, we see that the main beams are highly correlated. There are some differences in the side lobes. However, since the main beams are well matched, we would expect to be able to cancel main beam clutter. So this is an f over d of 1. Next, what we want to do is show the far field patterns of the 2 phase centers. Here are the far field radiation patterns for the DPCA dipole phased array before nulling. We see that the main beams are well matched. This is an f over d of infinity. And so these are plotted versus probe angle theta from minus 60 to plus 60 degrees. We see good agreement in the main beam. There are some differences in the side lobes. So now we compare the near field and far field simulated radiation patterns for the DPC array before nulling. And so what we're showing here for phase center A and phase center B is that we have a main beam formed and side lobes, and that the far field simulated pattern and near field simulated patterns look very much the same, except for some small differences in the first side lobes. Now what we're going to do is introduce 7 clutter sources spread over the main beam with total power 40 dB above receiver noise. We're going to put clutter sources in the main beam of each of the phase centers. We're going to put one large jammer 50 dB above noise at theta equal minus 20 degrees, or 20 degrees from broadside. in both phase centers. And so if we go through the adaptive DPCA nulling process, here are the near field and far field radiation patterns after nulling. The patterns on the left are for a stationary target. The patterns on the right are for a moving target with phase shift of 180 degrees and 1 PRI. So on the left, we're showing that when we go through the DPCA adaptive phased array signal processing, and since the main beam shapes were highly correlated, the clutter is suppressed. We see a null formed in the direction where the main beam was. We see a null formed at the jammer location. And the cancellation is 49.3 dB in the far field case and 48.0 dB in the near field case. So the adaptive array cancellation is approximately equal. They're not identical, but for all practical purposes, what we're showing here for far field and near field cases is that the clutter and jamming are canceled in a nearly equivalent fashion. So this is for a stationary target with phase shift of 0 degrees. If the target is moving at 180 degrees of phase shift in 1 PRI, we would see the full gain of the array both in the far field and near field cases. So we get full gain at the target position, and that would allow us to detect the target. So in this table we're showing the near field simulated interference to noise ratio before and after adaptation and the cancellation, and the same for the far field. So we're starting out with 50 dB interference to noise ratio before adaptation. After adaptation in the near field we reduce the interference down to 2 dB. In the far field the simulation shows that the interference was reduced to 0.7 dB. So the cancellation summarized here shows that there's about a 1.3 dB difference in the adaptive array cancellation. And so the adaptive cancellation is approximately equivalent for the near field and far field cases. This slide shows the consumption of degrees of freedom of the DPCA array in terms of the covariance matrix eigenvalues. And so in this example we had 7 auxiliary channels and a main channel in each phase center. So there were 7 degrees of freedom in each phase center times 2, so it would be 16 eigenvalues or 16 degrees of freedom in the covariance matrix. So this plot shows the amplitude of the eigenvalues versus index for the 16 eigenvalues. We see there are 2 large eigenvalues corresponding to the large jammer signal. There are a number of intermediate eigenvalues due to the clutter sources and the finite bandwidth, with the remaining eigenvalues at the receiver noise level. And notice that the near field eigenvalues at f over d1 are approximately equal to the far field eigenvalues f over d of infinity. And so we would conclude that the eigenvalues are approximately equal for near field and far field interference. And so the degrees of freedom that are consumed are approximately equal in the near field compared to the far field. So let's summarize. In this lecture we've investigated the focused near field adaptive nulling technique in terms of suppressing jamming and clutter and detecting targets. We've shown an equivalence between focused near field adaptive nulling and far field nulling. We've included mutual coupling effects. We've shown that the radiation patterns, covariance matrix eigenvalues, which are the degrees of freedom, and the adaptive cancellation show a near field far field equivalence. And so we can use this technique to evaluate the performance of a large adaptive antenna in the focused near field region. Chapter 5 of the book, Adaptive Antennas and Phased Arrays for Radar and Communications, contains additional information to supplement this lecture.